Welcome to Ecology, Biomes and Ecosystems Part 2, and the focus of this video is to talk about biogeochemical cycles and their impact on the environment, both on abiotic and biotic components. And we're going to spend time kind of looking at every system, but this is the slide that I ended on in the last video series, and I just want to talk a little bit more about this slide. So this shows the interaction between these geological processes, abiotic factors, and organisms, and understanding that this matter cycles through the earth in various ways. It cycles through the earth in a number of processes. You're probably most familiar with the water cycle, the carbon cycle, the nitrogen cycle, the least known cycles being phosphorus and sulfur, but also the rock cycle. And these cycles, along with the sun's energy, provide the base resources for producers. And the producers are the ones that are able to transform this matter and this energy from the sun into usable energy for everybody else. And that's the main concept that's the takeaway here for this video today. Understanding that all these cycles, in addition to the energy from the sun, make it possible, these are the base resources for all producers, in order to make them into usable energy for all the rest of us. And so we're going to study them in a little bit more depth. So first we're going to look at the nitrogen cycle. And what's critical is the fact that you can't replace these bacteria in the nitrogen cycle. This link, and there's an article that I'm asking you to look at about Biosphere 2, and your teacher has the link to that. But back in the 1990s, they tried to create this Biosphere 2, and it was a failure, and it explains why. And this bacteria is very critical in being able to make these conversions or these transformations of the nitrogen from something that we can't use or other organisms aren't able to use, or a lot of organisms aren't able to use, and to be able to convert that into something that is very usable for them. And so these bacteria aren't replaceable, and it's really important to understand that, and understand that you have this denitrifying bacteria that's going to convert nitrates back into nitrogen for the atmosphere. You have nitrifying bacteria that create that transforms nitrites into nitrates. This nitrifying bacteria also has the ability to convert ammonium into nitrites. So this bacteria in the nitrogen cycle is not replaceable, and it's very important to understand that. And this is a global cycle. So what I'd like to do is just go through a little diagram with you here, a little animation I have. And so here's what's important to do, and I like having the N2 together. So first of all, nitrogen is diatomic. There are 7 elements from the periodic table that are diatomic, and all that means is that they don't exist by themselves. N2 is a diatomic molecule, a diatomic element, meaning that it always exists in pairs, just like oxygen. And so plants and animals can't use this N2, so it has to be fixed into a form that's usable for us. Lightning can fix N2, and what that does, it allows nitrogen to combine with oxygen to form nitrate, which is NO3. This NO3 is going to enter the soil, and it can be absorbed through the plant roots, and the plant uses the nitrogen to form other compounds. And you studied this when you studied macromolecules, that's where this nitrogen is coming from. The N2 can also enter the soil. The nitrogen gas can enter the soil, and you have these plants, and some of these plants have special root nodules, like the soybean plant. And bacteria in the root fixes the N2, or the nitrogen gas, allowing nitrogen to form other compounds. And now the plant can use this nitrogen. So what happens is this bacteria in the root nodules makes the nitrogen a usable form for the plant. Then the little organism can come and eat the plant, and it can get its matter from the plant. Bacteria in the soil also fix nitrogen to form other compounds that can be absorbed as well. And animals like the vole eat the plant to get the nitrogen they can use to build within their own system. Again, when I'm talking about why we're using these ends, this is where the end's coming from when we were talking about in biochemistry in year 1 bio, where you had carbon, oxygen, hydrogen, and nitrogen being the most prevalent elements that you use to build carbohydrates and nucleic acids, lipids, and proteins. Okay. And then as this organic matter decomposes, the nitrogen compounds return to the soil. So the plant dies, and they go back into the soil. And other bacteria in this soil are able to break down this nitrogen and into nitrogen gas and return it to the air. And so that's a simplification of what happens. But I wanted to go through the chemical part of how this occurs. Talk about the N2, just like the O2, is always going to be in pairs because it's diatomic, and make sure that you're comfortable with that. The animation is listed, so your teacher, if she wants to go back over it with you, can. Now we're going to move on to the phosphorus cycle, and unlike the nitrogen cycle, which has an atmospheric component, phosphorus does not exist in the atmosphere. So phosphorus tends to be fairly localized. And at the end of going over these cycles, I'm going to show you where things can go wrong. But the phosphorus cycle, because it cannot exist in the atmosphere, it takes a long time to cycle, as opposed to the other cycles, the water cycle and the nitrogen cycle and the carbon cycle, which all have a atmospheric form or a gaseous form. And so phosphorus is not really a global cycle when you think about it, because it can only exist in liquid or solid. Now let's take a look at a little animation of this. Oopsies.
Are mined for use in the manufacture of fertilizers and detergents. During weathering processes, phosphates are leached from sedimentary rocks and deposited into the soil or bodies of water. Guano is washed by water into the ocean. Land and marine plants uptake phosphates from the soil or water. Animals uptake phosphorus by eating plants or plant-eating animals. Bacteria decompose dead land and marine plants, and marine birds excrete phosphate-rich guano. Sedimentation involves the deposition of phosphate-rich materials in the sediments of marine environments. They become buried and compacted into sedimentary rocks.
So this just showed a brief animation of the phosphorus cycle. I want to show you a second one too, just because I think that this is a cycle most students aren't familiar with.
The main reservoirs for phosphates are ocean bottom sediments and terrestrial rocks. By weathering and soil erosion, phosphates from rocks enter streams and rivers and are then carried to the oceans. Here, phosphates settle out and accumulate as part of marine sediments. Over millions of years, movement of crustal plates uplifts the seafloor and the phosphates become exposed as terrestrial rocks. With time, weathering and erosion releases the phosphates, beginning the geochemical phase of the cycle once again. The ecosystem phase of the cycle is more rapid than the geochemical phase. On land, plants take up dissolved phosphates from water in the soil. Herbivores get phosphates by eating plants. Carnivores get them by eating herbivores. Decomposers get phosphates by breaking down wastes and dead organisms. Decomposition releases phosphates to the soil, where they become available to plants once again. In marine ecosystems, phosphates are taken up by plankton, which form the base of ocean food webs. Death and decomposition of marine organisms release some phosphates to the water. Phosphorus-rich shells or other hard parts fall to the ocean floor and become part of the marine sediments. The excretions of some oceanic birds form another phosphate-rich resource. Their droppings accumulate on islands as guano. Weathering of guano deposits returns phosphates to the sea. Phosphorus circulates through water, the Earth's crust, and living organisms. There is no atmospheric component to the phosphorus cycle. Human activities are altering the phosphorus cycle. Phosphate is mined from deposits found mainly in shallow coastal waters. This phosphate is added to fertilizers for crops and enters land food webs. Some of the phosphate ends up in lakes and rivers through erosion and runoff. Excess input of phosphates can disrupt aquatic ecosystems, especially lakes.
Okay, and we're going to talk a little bit more about that at the end of this slide. So again, what's important to understand about the phosphorus cycle is that the geochemical cycle takes a really long time and that there's no gaseous phase or atmospheric component. It only exists in liquid or solid state. Therefore, it doesn't enter the atmosphere. Let's take a look at the water cycle. And we'll go, this is probably the cycle that most students are very familiar with. What's important to understand about the water cycle is that as it changes, it can have an impact because this is a global cycle. And water, of course, exists in 3 states, liquid, ice, and vapor. And the sun is the driving force of this cycle. And the amount of water that's on Earth stays fairly constant, but what changes is its distribution among these 3 states of liquid, ice, and vapor. And climate change, we talk a lot about the disruption of the water cycle. But let's take a little video, a little look at an animation about this. So how does it move? So basically, I think you're very familiar with how the water cycle moves. And what's important to add, I think you're very comfortable with capillary action being taken up by the plants, evaporation, freezing, condensation, precipitation, infiltration, and runoff. What's important to understand is where water is used, and when we move water from one location to another, like a far geographic distance, what happens, and where it exists. And so what can happen here is that every time water passes through any of these components, it can pick up other things that can be problematic. So in other words, if they're drilling on this mountain or mining for something, you can have an impact that could be problematic as that water cycles, because now the water is not just pure water, it may have other things in it. And it's also important to understand that if we lock water up where it's not moving through this cycle, then it becomes unavailable as a resource for us. Okay, so I think the water cycle, I'm not going to hit that too hard because I think that's the one y'all are the most comfortable with. All right, let's look at the carbon cycle. And so the carbon cycle involves cellular respiration and photosynthesis, which obviously has the component of the sun for photosynthesis. And what happens is that producers are able to take energy, photons from the sun, with carbon dioxide and water, and convert them into chemical energy that can be used by other organisms. Primary consumers eat the producers, and then a higher level consumer eats that producer. Their waste, or when they die, is utilized by decomposers. And then you also have this soil component going on, and as I mentioned, those soil microbes and the bacteria that's in the soil that's able to help convert things back and return them to the atmosphere. We also have anthropogenic or human things that can impact the carbon cycle. As you see this little factory off to the side, you're having wood and fossil fuels being burned, and because of that you're having additional carbon dioxide released into the atmosphere. So let's take a little look at a simulation for this. And I just want you to look at the chemistry of this for a minute, and I'll talk a little bit about it. So, you know, when you're burning and you have forest fires, you're releasing the CO2. You also can have the CO2 dissolved into the water. You can have CO2 dissolve into the soil through decomposition. You have CO2 exiting, being taken up by the plants, and oxygen being released by the plants. But it's important to see in this picture that you have this interaction of human things that are going on with the fossil fuels and the forest fires, which may or may not be human caused, because certainly forest fires can or fires can be created in nature all on their own without our help. But you have this interaction between organisms of all kinds, as well as man-made issues that create an issue with where carbon dioxide is getting locked up or creating what we call a carbon dioxide sink. So I just wanted to show you the movement of these CO2 molecules and have a little conversation about that interaction. Again, it's very complex in how they interact with each other and what biotic and abiotic factors are available in that area in terms of helping or hurting this cycle, making this cycle less efficient, or more sustainable or less sustainable as you move through it. Okay, let's talk about the rock cycle, often missed because biology teachers don't talk a lot about the rock cycle. But the rock cycle has a tremendous impact on the minerals that are available to us and how we move things throughout the earth. And so first I just wanted to remind you of the three types of rock: sedimentary, metamorphic, and igneous. And it's not important that you know specific types of those. It's just important that you understand what the agents of erosion are, because erosion is what's going to transport something from one place to another. Weathering is the breakdown of material. And so when something's weathered, it weathers in its place. It doesn't go anywhere. Erosion is when we move something from one place to another. And oftentimes when things go bad or we have a negative environmental impact, it's because of one of the agents of erosion has moved a mineral or a group of minerals or sediments or different types of rock into an area, and the weathering of those in that area impacts the soil and thus can have a strong impact on all the other abiotic and biotic factors in that area. And so one of the things I like to talk about really briefly is the rock cycle, just so we don't forget that this erosion is what can move material or matter from one place to another. And that can be of significant import, positively and negatively. Oftentimes we talk about it in a negative sense, to be quite frank. But let's take a little look at this rock cycle. I just want to go over some of the processes really quickly. And so I'm just going to point on the areas. And so the red arrows produce igneous rocks, and this is melting and cooling. So generally we have a lot of igneous rocks where we have severe climate. So volcanic activity or activity where you're having uplift from the ocean floor, things like that. The green arrows are arrows that are going to produce sedimentary rock. This is uplift of the Earth's surface, weathering and erosion, transportation, deposition, and cementation can produce sedimentary rocks. And then the purple arrows are showing what produces metamorphic rocks. And this is exposure to heat and pressure. And again, I don't want you to memorize these. I just want you to understand that they have an elemental component in what's going on in the earth through erosion. Another cycle I wanted to touch on really briefly was the sulfur cycle, because that has an issue too, and mainly because you're going to get the sulfur from it, which can be a component of acid rain. And it's showing a tree and the organic matter decaying, and what's going on here is that this is reacting with water and oxygen, and as it reacts with water and oxygen, this sulfite, it can create acid rain as it reacts with them and falls to the earth. And it can also react with oxygen in the soil the same way. And so what we can do is create this issue where we have sulfur in the soil and the atmosphere. So let's take a look at this animation.
Hydrogen sulfide gas is released into the atmosphere by volcanic eruptions, hot springs, and anaerobic decay of sulfur-containing biological material in swamps, bogs, and tidal flats. Certain marine algae produce dimethyl sulfide, a volatile compound that enters the atmosphere as tiny droplets. Sulfur dioxide gas is released into the atmosphere by volcanoes and also forms when dimethyl sulfide reacts with oxygen gas. The burning of fossil fuels, such as coal and oil, releases sulfur dioxide into the atmosphere. Sulfur dioxide reacts with atmospheric oxygen to produce sulfur trioxide. Some sulfur trioxide reacts with tiny water droplets to form sulfuric acid. Sulfur oxides also react with ammonia to produce tiny particles of ammonium salts. The winds carry droplets of sulfuric acid and particles to sulfate salts, which then fall to the earth in acid deposition. By adding sulfur compounds to the air, the use of fossil fuels increases the rate of acid deposition. All living things require sulfur to make proteins. Plants get sulfur by taking up ions of sulfate salts from the soil. Animals get sulfur by eating plants, and all living things release sulfur compounds when they decay. Decomposition releases sulfate salts, which can be taken up by plants, as well as gaseous hydrogen sulfide. Some hydrogen sulfide enters the atmosphere, but when decay occurs in an oxygen-free environment, anaerobic bacteria break down hydrogen sulfide and release sulfur gas. Oxygen-requiring bacteria can incorporate sulfur into sulfate salts, which can be taken up by plants and enter the food chain once again.
Okay. So again, the chemistry of the sulfur cycle is not important, but what is important to understand is that it can have an impact, both positive and negative, but we do need small amounts of sulfur in our diet. Okay, so let's overall take a look at what we've been looking at. So we have this organic matter that's available as nutrients, and we have a bunch of different things going on here on this slide, but to understand this slide completely will be really helpful to you. So we have this two-way reaction between inorganic materials and organic materials. And so these inorganic materials available as nutrients are in the atmosphere, in the soil, and the water. And we can have them come in as respiration, decomposition, and excretion, and they can leave to go to organic material or living organisms through photosynthesis and assimilation. Then we can have this fossilization occur, where we create coal and oil and peat over a long period of time, and when this fossilization occurs, these nutrients are now no longer available. And that's an important concept to understand when we talk about fossil fuels, because it takes millions of years to make them, but when they get locked up, they're no longer available in our system. And because of the conservation of matter, this is all we have, and this is all we're getting, what is here on Earth. And so what we do is we have erosion that can move these organic materials and make them available, or we can have the burning of fossil fuels, which goes back into how these organic materials become available again. And then we also have a back and forward process between the atmosphere, soil, and water, and minerals that are in rocks. And minerals in rocks can occur with weathering and erosion, and they can also form sedimentary rocks. Okay, so after we finish looking at the cycles, I just want to talk about the mass and the metabolic rate and the size of the organisms, just really quickly to touch on this, because the biological systems utilize free energy, and they utilize this free energy and this material to grow and reproduce and maintain their own dynamic homeostasis. And so what's important to understand is that all these organisms require a constant input of energy, and that they're capturing and storing this energy for their own processes. And so their mass is tied to their metabolic rate. And so smaller organisms obviously tend to have a lower metabolic rate. They have less energy input required, whereas larger organisms, depending, have a higher metabolic rate. And it's important to understand that organisms are always trying to obtain energy so that they can use it for their biological processes. And it's also important to understand that organisms must exchange matter with the environment in order to grow, maintain their own organization, and reproduce. And so this slide just kind of wraps it up in terms of energy and how this works. So you have this gross amount of energy, and then you have the energy used to obtain that energy. And with that, then you end up with this net amount of energy that you have the surplus of, that you're able to use to do these things for your body. to maintain your body, to grow, to store, to protect yourself, to have the energy to be able to run away if something's after you, and then also to reproduce. And so this is tied back into fitness, because you have to have an energy surplus beyond normal living processes in order to have the ability to reproduce. And it's important to tie that back to that at the end. So we live in this biosphere, which is, all the living parts of the earth, all the living things on earth. And what happens when one of these cycles goes out of balance? Well, a cycle can go out of balance because of man-made reason. It can also go out of balance because of a natural phenomenon. And it's important to understand that not every imbalance is the result of man-made problems. It's also important to understand that sometimes it goes out of balance as sort of a cleansing. So additionally, this may just be the natural state of that ecosystem, and as a consequence of how they move nutrients and the availability of those nutrients. So I'm going to give you an example involving freshwater habitats, and how you can have issues there. So the one we're really going to look at is eutrophic waters, which have high primary productivity. But I wanted to talk about their polar opposite, which is oligotrophic waters, which have low primary productivity. And the reason why these lakes that have this low primary productivity, which are on the left, they're very cold and they just don't have a lot of nutrients available to them for whatever reason. And so they don't have a high sustainability of organisms in this. And then you have eutrophic, which is on the right side of the slide. And this almost looks like a green blanket over this lake. And what caused that? Well, in the earlier video, it was talking about how we dig up this phosphorus. And we use phosphorus and nitrogen in various fertilizers and detergents and things like that. And when these run off into the lakes, they actually can provide too much of a food source for the algae. And so what happens is you get this algal bloom, is another term for it. And these nutrients cause this increase in this phytoplankton. You get this algae bloom, which is pretty much cuts off the oxygen in the water, which we refer to oxygen in water as dissolved oxygen. And then also because it's very oxygen demanding, and then as the algae dies and it's decaying, it's also demanding more and more oxygen. So the oxygen in this water system is really being consumed by the algae and its life processes, and because of that, it's not available to other organisms. And so when you have a system go out of balance, it can be problematic. So let's take a little look here at eutrophication. And so what happens is these excess nutrients from fertilizer, and again, detergents used to have them in there. And you think about that because the phosphorus cycle is generally not very fast. That we used to use phosphorus in our detergents, we added a lot of phosphorus to the cycling system, and they go into these streams and then downstreams into the bay. You also can have farm animals that do not process all the food they eat, and their excrement is passed on also as runoff and through their digestive system, and then they poop, and rain washes this nitrogen and phosphorus into the bay as well. And we can look at this molecularly if we wanted to on this, but what's just really important to understand, this is the microview of the algae and bacteria that are naturally present in small amounts, but what happens is they get this huge abundance of food source and they go crazy. So this algae grows in the water, and it's limited by the amount of nutrients that's present, but the algae grows quicker when the nitrogen and phosphorus are available. And when this happens, we get this algal bloom. And some of the things that used to prevent these big algal blooms, like these buffering plants, as you see in the slide, that would have helped prevent them, these estuaries or these marshes, we have torn down. We didn't understand the importance years ago in having these for floods and for also helping take out some of the nitrogen and phosphorus before it hit the bay. And so what happens is you have this algal bloom, and it's literally a bacteria buffet. And the bacteria break down and consume this dead algae. And as more and more of this nitrogen and phosphorus come in, they use the oxygen in the water to respire and release carbon dioxide, and they leave very little oxygen, dissolved oxygen, for other organisms. So if the dissolved oxygen can't be replaced quickly enough, the oxygen level becomes so low that while the bacteria are having this lovely buffet, the other organisms in the water are not getting enough oxygen and they die. And the dissolved oxygen can eventually return to the system through photosynthesis and turbulence, meaning that if you had an algal bloom and then you have a really heavy rainstorm, that can actually be helpful because that can create turbulence and break things up and move things along. But it takes time for this to happen. And so if you wanted to go back over this slide, you can, but I think that does a really good job of explaining when things go wrong. And so here I'm showing you live pictures of algal blooms. And I live right in Richmond, Virginia, and we tend to have a huge problem with this, especially in planned neighborhoods, because in planned neighborhoods, they tend to have very nice lawns, and a lot of people over fertilize. And when you have this over fertilization, that nitrogen and phosphorus is going to run off. And that's going to be a problem, as well as the fact that we do a tremendous amount of pig farming and chicken farming in Virginia and North Carolina, so we tend to have a lot of excrement from that as well. So we do tend to have natural algal blooms that occur here in the summer because of over fertilization in our planned neighborhoods. So some of our man-made lakes are very green. And definitely not places where you're going to find a lot of organisms besides bacteria. So that's what can happen when a system goes wrong. All right, so let's look at some data from this. So this is some data that we collected on a river, and it was collected in different rivers in Virginia. I took it off of one of our websites where we get data. And I just pulled some random stations and took down the dissolved oxygen, the pH, and the temperature. And what we're going to do is use your conversion sheet. You're going to have a formula sheet on the test this year. And what we're going to do is we are going to, for station 1, we're going to calculate the primary productivity of a water sample. And we're going to report that answer in units of milligrams of carbon fixed per liter. And so I've put the little equation off of your formula sheet that you're going to want to do. And you're going to want to stop the video here and work this problem out. So for station 1, you need to calculate how many milligrams of carbon are fixed per liter. So you should pause the tape. And if you want to practice this equation, you could do it for all 14 stations. But on the next slide, I have shown you how we've done that. So for station 1, the dissolved oxygen rating was 4.2 milligrams of oxygen per liter. We multiplied that by 0.698, which was on your student formula sheet, to come up with 2.9 milliliters of oxygen per liter. And then we multiplied that by 0.526 to get 1.6 milligrams of carbon fixed per liter at station 1. And as you can see, I made a second column here where I've put all the answers for stations 2 through 14, which if you want to practice with this equation, I highly recommend it. It's called the primary productivity calculation, and it is found on right below rate and growth on your student formula sheet. No need to memorize this. You will have this formula sheet during the test. So this concludes ecosystems, cycles, and impacts. Thank you.